Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 9, Bonus Material. In our main lesson, we considered growth rates of functions and ordered them in a hierarchy as x goes to infinity. This led to a language for discussing and controlling that growth, both as x goes to infinity and as x goes to 0. This language is called Big O. Before we get to that, there's one thing that we need to reconsider a little bit. One of the things we discussed was the factorial function, or factorial growth. But what exactly do we mean by factorial functions? What is x factorial when x is not an integer? Well, there is a real definition for it. It's going to look a little complicated. The definition of x factorial is the integral as t goes from 0 to infinity of t to the x times e to the minus t dt. Oh, what in the world is that? Well, we're not going to explain that now. We'll get to that later in this course, maybe in Chapter 3. But for the moment, one thing to know is that this definition satisfies the property that factorials have, namely that x factorial equals x times quantity x minus 1 factorial, at least for x positive. And also, n factorial, for an integer, agrees with this definition. Now, I'm not going to prove that now. We'll talk about that later in the course. What I want to argue is that this factorial growth beats exponential growth. In the case where x is an integer, a positive integer, then we get x factorial being the familiar x times x minus 1 times x minus 2, etc., all the way down. If we look at e to the x, well, this is some number of copies of e multiplied together. Now, for values of x very large, we see that terms in the numerator and terms in the denominator pair perfectly, and almost all of the terms in the numerator are much bigger than the terms in the denominator. And this means that in the limit, as x goes to infinity, we get something that is infinite. That means that x factorial grows much faster than e to the x. If you're curious about this unusual sort of definition, look up information about the gamma function. We'll return to that a little bit later in this course. What I'd like to spend some time on is a bit of discussion about Big O. How is this language used? Why is this language used? It is ubiquitous in applied mathematics, and you're going to see it at various points throughout this course. So let's take some time and review and extend what we know. Recall that a function f is said to be in Big O of a function g if, in the appropriate limit, f in absolute value is less than g in absolute value times some constant c. We don't care about what the constant is. We just want to know that there is some upper bound. Again, this holds in the limit as x is going to wherever we're interested in looking at. Maybe x is going to 0, or maybe x is going to infinity. One of the reasons Big O is so useful is that it forms an efficient language. For example, f is in Big O of 1 means the same thing as saying that f is bounded in the limit as x is going to 0 or infinity or whatever. There are other applications as well, real applications. For example, in computer science, one is often interested in specifying how much effort it takes to execute a certain algorithm. This is the subject of computational complexity. Consider the following. Let's say you have two n-digit numbers, and you want to multiply them together. How much work are you going to have to do? How many individual mathematical computations is that going to take? Well, let's consider what it takes to multiply two numbers together using the standard algorithm that you learned in primary school. And let's count this as a function of n, and consider what happens as n is going to infinity. To multiply these two numbers together, I need to take each digit of the second number and multiply it by the entire first number. That is n elementary mathematical operations. Well, maybe it's not n. Maybe we should call it 2n because of the fact that you have to multiply 6 times 3, 18, write the 8, carry the 1, etc. We'll pick some constant times n, but we need to do that for each of the n digits in the second number. Well, we're still not done because we need to take all of those resulting products and add them together. And I'll let you try to figure out how much effort is involved in that addition. It's, some number times n times maybe n minus 1. I don't know. I'm not a computer scientist. I'm a mathematician. But neither I nor the computer scientist needs to worry about these exact constants. If all we care about is what happens as n is going to infinity, we can say that this algorithm is in big O of n squared. It's going to take a quadratic amount of effort. So as your numbers get bigger and bigger, you're doing a lot more work to multiply them together. Is there an algorithm that is better, that is, say, n times log n? Well, that is what big O is good for. Error analysis in engineering, physics, other sciences is another excellent application. Let's say that you know the kinetic energy of your body is 1/2 the mass times the velocity squared. But let's say that your measurement of the velocity has some error associated with it. Epsilon, we'll call that error, and we'll assume that epsilon is very small. What is the induced error in our kinetic energy? Well, of course, if we expand that out, 1/2 mv squared plus m times v times epsilon plus something that is in big O of epsilon squared. What we really care about is the leading order term in epsilon. That is going to dictate what the error to the kinetic energy is. And we can see that that is really the momentum, m times v in this case. Now, other examples are relevant to what we began this lesson with. Let's consider x factorial. We argued that its growth rate is pretty big, that x factorial is not in big O of e to the x. But we can say more. There's a wonderfully useful and powerful formula in mathematics called Stirling's formula that says exactly how fast x factorial grows. One form of this says that log of x factorial equals x times log of x minus x plus some remainder term that is in big O of log of x. Perhaps the stronger version of Stirling's formula will be a bit more transparent. It says that x factorial equals square root of 2 pi x times quantity x over e to the x power times 1 plus something in big O of 1 over x. Now, you don't need to memorize either of these. They're wonderfully useful in probability, in combinatorics, in lots of areas. But what I want you to see is that the appropriate language for expressing how fast x factorial grows as x goes to infinity is big O. Pure mathematics uses big O as well. If we define the function pi of x to be the number of prime numbers less than x. Let's restrict to positive primes, of course, and x is going to be, let's say, integer valued. Doesn't matter. Then, one thing we could say is that the number of primes is big O of x. But that's a vacuous statement. Not every integer is prime. We'd like some idea of how many primes there are. Well, of course, there are infinitely many primes, but we'd like to know a bit finer information. What kind of density do the prime numbers have within the natural numbers? Well, we can use the language of big O to state the prime number theorem, which says that pi of x is to leading order x over log of x. And that's not exactly what it is. That's just the leading order term. But pi of x is x over log x times quantity 1 plus something in big O, 1 over log of x. That's one example of how this language appears in everything from pure mathematics to applied mathematics to the physical and computational sciences. It'll take a little while to get used to this language. It's going to take a bit of practice. Most students find it a bit unlike things that they've learned in the past because of this arbitrary constant. But do a few practice problems, and you'll see big O cropping up later in the course.